This is a $500 million engineering masterpiece, but at 35,000 feet it ceases. Pressurized isolation. Pod fighting brutal physics to survive up here. Engineers had to redesign the structural skeleton from scratch. Because at cruising altitude the atmosphere is actively trying to rip this structure apart. The impact of high altitude jet streams hits the airframe with thousands of pounds of percussive force. If this internal framework were completely rigid, the concentrated tension would snap the beams like brittle glass, so it is engineered to do something that looks terrifying. It bends to displace the energy to lift a 500,000-pound aircraft into the sky. Engineers don't fight gravity, they manipulate the air itself. By slicing the wing open, we reveal its secret weapon. The airfoil shape, because the upper surface of the wing is curved. The air molecules rushing over the top are forced to travel much faster. This difference in fluid velocity triggers a fundamental law of physics. Fast air creates low pressure above. Slow air creates high pressure beneath. The high pressure underneath literally pushes the wing upward. This is the mechanical reality of lift, but generating lift in a sterile lab is simple. Sustaining it during a violent atmospheric storm is where engineering prices skyrocket. At cruising altitude, the plane encounters severe turbulence, chaotic pockets of air trying to snap the structure. If these wings were built out of rigid traditional aluminum, they would instantly fracture and snap under this stress. Instead, they are woven from advanced carbon fiber composites, allowing the wingtips to flex upward by an impossible 26 feet. They act as giant shock absorbers, flexing to protect the cabin and ensure the ride remains perfectly smooth. But lift means nothing without the raw thrust required to smash through the atmosphere in the first place. For that, we must step directly inside the center of a non-stop mini inferno. To be a luxury playground, it becomes to generate 100,000 pounds of thrust. This engine sucks in an Olympic-sized swimming pool of air every single second. The process begins at the intake fan, spinning at thousands of revolutions per minute. This spinning mass accelerates incoming air particles, ramming them directly into the core. Here, multi-stage titanium compressors squeeze that air down into a space 1/30th of its original volume. At maximum pressure, jet fuel is injected and ignited, triggering a non-stop violent explosion. The internal temperature spikes to over 3,000 degrees Fahrenheit, hundreds of degrees hotter than the melting point of the metal itself. Without an intervention, the entire engine would liquefy from the inside out within minutes. To prevent total failure, engineers drilled thousands of laser-precise holes directly into the blades. Relatively cool air is pumped from the inner core out through these microscopic passages, creating an invisible fluid barrier that insulates the metal from the absolute fury of the fire. This boundary layer is all that stands between flight and a catastrophic mid-air inferno. With the thermal threat contained, the engine can safely unleash its full mechanical fury, forcing the jet through the atmosphere. But while the engines handle the heat of the outside world, an entirely different battle is brewing inside the cabin.
Inside the cabin, passengers sit in total luxury, but outside these walls, the air is so thin that a human would lose consciousness in less than 15 seconds. To keep passengers alive, the cabin must be heavily pressurized, turning the airplane into a giant metal balloon. But when a structure expands, physical stress seeks out the path of least resistance. In early aviation, these sharp 90-degree corners concentrated the stress so violently that the fuselage would literally rupture. Mid-flight, the solution required a complete reimagining of geometric design. Engineers eliminated the sharp corners entirely, smoothing them out into flawless, continuous curves by rounding the edges. The internal pressure is no longer trapped It flows effortlessly. Around the perimeter, this single geometric breakthrough turned every passenger window into an oval, saving thousands of lives at 40,000 feet. The pressure differential between the inside and outside is a constant, invisible war, but with rounded geometry. The airframe achieves perfect mechanical equilibrium, turning the ultimate threat into a non-issue. Yet, holding the aircraft together at 40,000 feet is only part of the journey. The final, most dangerous challenge is returning a 500,000-pound mass back to the Earth. Landing an airliner means dropping a 500,000-pound mass out of the sky and forcing it to collide with solid concrete at 140 miles per hour. The entire weight of the impact is directed into a single mechanical focal point. The main gear struts. These struts are filled with high-density hydraulic fluid, engineered to absorb millions of foot-pounds of kinetic energy. As the fluid compresses, the physical force is transformed into an intense concentration of mechanical stress. But before that energy ever reaches the struts, it must pass through the only components touching the runway. The instant of contact triggers a massive spike in frictional heat, threatening to ignite the tires. Regular air contains oxygen and moisture. Under this extreme heat, that mixture would expand rapidly, causing the tires to explode. To prevent catastrophe, aircraft tires are inflated exclusively with pure, bone-dry nitrogen. Nitrogen is completely inert. It absorbs the heat without expanding, creating an unyielding chemical shield against explosive failure. By mastering the chemistry inside the tires and the hydraulics in the struts, the airframe tames the collision. From the flexible skeleton to the thermal shields, every system works in absolute harmony now. Let us piece the masterpiece back together and witness the ultimate synthesis of engineering power. Every invisible force, every geometric breakthrough, and every ounce of structural resilience converges into a single, unified machine designed to defy the laws of nature. From the flexible wing spars to the rounded oval windows, the invisible design becomes visible reality. The smooth metal skin slices through the atmosphere, minimizing drag and guiding the airflow with absolute mathematical precision. Lift, thrust, weight, and drag all acting in a state of flawless engineered harmony. A $500 million masterpiece, transforming the sky from a hostile vacuum into a smooth highway. But to understand the future of flight, we must always return to the core engineering and strip away the metal to look at the invisible forces that govern the sky, because every great journey begins exactly where it ends, with a single line of code and a blank slate. What do you think? Tell me below in the comments and subscribe for more like this.